The next section of the book that we're going to be going over is section 15.2, the physics of music. So we're talking about sound. Remember, it's a longitudinal wave. So the main idea that we have here is that music consists of a complex sound waves produced by vibrating objects. And they show the trumpet or cornet, which happens to be in the picture there. And the question then becomes, vibrating object? How does it vibrate? Well, you're going to find out that with the trumpet, it's the vibration of the lips. And what's interesting is that when you vibrate your lips and you blow, you're getting all the frequencies out. But then how do you get the particular sounds? Well, that's what this chapter is about. First of all, sources of sound. As it says at the yellow there on the left-hand side, recall that sound is produced by a vibrating object. And the vibrations of the object create particle motions. And so you get that pressure oscillations, the back and forth, which happens. And anything that's going to give sound is going to have that sort of oscillation. As it shows in the blue, you can have a cone, a loudspeaker to do that, or you can have a musical instrument with congs or cymbals and drums. All sorts of things will cause that. We have a thing which will vibrate, which is our vocal cords. And on the right-hand side, it talks about that a little bit. And so the frequency of vibration is controlled by the muscular tension placed on the vocal cords. The more tension on the vocal cords, the more rapidly they vibrate, resulting in a higher pitch sound. And if they're more relaxed, they vibrate more slowly and produce lower pitch sound. So it's really all in the tension that you have within your particular vocal cords. Then we get into different instruments like brass instruments, woodwind instruments, things like that. There's also stringed instruments that it talks about: piano, guitar, violin, things like that. So let's go on to the next page. Now, what we're going to find is that when we take a look at this, we have resonance in air columns. So what occurs is when the instrument is played, and in this particular case, they're talking about a mouthpiece over a brass or wind instrument, like the trumpet that we saw on the front page. When the instrument is played, the air within the tube vibrates at the same frequency or in resonance with the particular vibration of the lips or reeds. Now what happens is you get all of the different frequencies, and what the tube will do, it will select which one it resonates with. Because once it resonates, then what happens is you get this huge wave which gets generated, which becomes extremely loud. On the right-hand side, you'll notice there's water with a tube on it. Keep paying close attention to that thing, because we're going to actually do that in a lab. We're going to be doing later on to figure out the speed of sound. So on that one, you notice the tube's in the water, and so it has an open end on the top, closed end on the bottom, and we call that a closed pipe resonator, a closed pipe tube. And what you generate is you generate these standing waves that will be that'll be there. And so what will occur is that once you've got a particular wave which goes down and comes back and resonates, then you're going to get a really loud sound coming from the object at that point. Now, on the left-hand side of the picture there, you notice it's closed because one side's open, the other side's closed. But if both sides are open, we call that an open pipe resonator because it's open on each end, which happens to be there. Now, with resonance lengths, as we start to take a look at this, you'll notice that the closed pipe, take a look at that particular on the right-hand side. You will notice that you have a pressure node on the top, and that actually is 1/4 of a wavelength. If you take a look at the open pipe, you'll see it's a half a wavelength. That's going to be really important for us. So the first one the closed pipe resonates to is going to be a 1/4 wavelength, and the first one for an open pipe is going to be a half a wavelength, which is there. And that's what it tells us right here. If a closed end must act as a node and an open end must act as an antinode, what's the shortest of column of air that will resonate in a closed pipe? Well, that's going to be our 1/4 wavelength. Now, every time, and we'll see it on the right-hand side there, you see the 1/4 wavelength. So the wavelength equals 4 times the length, because that's a 1/4 of the wavelength. So 4 times the length, you get the wavelength. Now, if you go to the next one, well, notice on that left-hand side, you've got that 1/4 wavelength. On the one right next to it, the lambda 3, then what you notice is we've added a half a wavelength, because what we're doing is we're adding a node to it, basically. Every time you go up, you add half a wavelength. That's for an open pipe or a closed pipe. And so you notice that the first frequency, that F1, which is the fundamental, 1/4. The second one, you add a half. Now remember, when you add halves to a fourth, you're adding 2/4. So what you get is 3/4. So F3 is 3/4. That's what's called the third harmonic. And then you're going to add another half for the next one, F5, 5 over 4. We're going to get into this a lot more. We just want you guys to be aware of what's happening. So as we continue on, we've got an open pipe. Now with an open pipe, you start with a half a wavelength, as you can see up on the top. Then what occurs, you get is that you add a half to get to the next one. So while the F1 is going to be V over 2L, because it's half a wavelength, the next one is going to be V over L, because half a wavelength and half a wavelength, one wavelength. And you'll notice that in the picture right above it. Then the next one, we add another half. So it's 1 and a half, 1 and a half. And that's why you get 3, 2, 3 over 2. And that is the third harmonic, which actually exists there. So now we realize that we have a quarter of a wavelength, which exists to start with a closed pipe, and a half a wavelength, which is going to be for a open. Now, strings. Take a look at the string there, and you'll notice something interesting. It says a string in an instrument is clamped at both ends, and therefore the string must have a node at each end when it vibrates. So it's the same on each end. Well, let's think about that for a second. In an open pipe, you have open, open on each end. In a closed pipe, it's closed on one end, open on the other. In a string, it's closed, closed. What's interesting is, if you take a look at the picture on the right-hand side of 999, you'll notice half a wavelength. So that means the fundamental, 1/2 the length, okay? The next one is going to be for the second, what's called the second harmonic. That's 2 halves, or 1. And then on that third one that's down there, you'll notice you add another half. Well, 1 plus a half, 1 and a half, or 3/2 the wavelength. Go back a second. That video which is there, we're going to take a look at that in class, but I'd recommend taking a look at that. It's pretty darn cool. Then what happens is we start getting into sound quality, and you can sort of just look that over. We're not going to get too much into that. But down here, this is what I was talking about before, and to get into it a little bit more. For a musical instrument, the lowest frequency of a sound that resonates is called the fundamental. That's the F1. It's the fundamental because it's the most basic. It's the fundamental. Now remember, with the closed pipe, that's going to be a quarter of a wavelength. So it's 1/4. And we call that the F1. If I'm going to add a half to that, well, remember, you're adding 2 quarters to 1/4. So you get 3 quarters. We don't call it 3 quarters. We just call it 3. We just use whatever happens to be in the numerator. And that's why you get the odd numbers. 1, 3, 5, 7, etc. Because you keep adding a half to it. Now, with an open pipe, you start with 1/2. Well, 1/2 plus 1/2, you get 1 or 2 halves. You add another half to that, that's 3 halves. That's why you get every number, F1, F2, F3, F4, because you keep adding a half to it. So now as we head on, they talk about consonance and dissonance. You can just sort of look that over. And then we get this thing called beats, an incredibly easy thing. I'm going to be showing you a particular demo on that in class and stuff. And with beats, what happens is if you get 2 tones that are really close to each other, you're going to get a wobble in it. It's going to wow, wow, wow. And we'll listen to that. But the big thing about it is the beats is super easy. All you have to do is take, as it shows there, F beat, the frequency of the beat, is the frequency of the first one minus the frequency of the second one. And then you take the absolute value. So if I had the first frequency was 150 hertz, and the second frequency was 152 hertz. Subtract 152 from 150, 2 hertz. Boom. And it's an absolute value. So that's what we're doing in this particular chapter. Keep